Hello, in this video we're going to talk about comparing conditions of a gas before and after some sort of change. This is contained in section 13.6 of your book. Okay, so the basic idea here is this, is that your ideal gas law, PV equals nRT, well, you can rearrange it to solve for R. And R is always a constant. So in any condition or state of a sample of gas, the pressure times the volume divided by the number of moles times the temperature is equal to some constant. So now if you have some change that's occurring to your gas, before and after this change, R is always going to be constant. And so you can label before the change with indices or subscript 1 just to identify here it is before. You can label, okay, here it is after the change. And then if you set these two R's equal to each other, then you can also set all of these P1 V1 over N1 T1. You can set both of those equal to each other. So then that leaves us with what we have down here on the bottom, that for any sample of gas, its pressure times its volume divided by number of moles times temperature is equal to that same collection of variables after the change. And so this is really handy. And you'll have an example problem here at the end of showing what you can do with this. But it's often easier to be able to simplify it even a little more. And so consider that if you're having some change in your gas and something is held constant, well, that number is going to be the same on both sides of this equals sign, and then you can just cancel it out. So very commonly the number of moles of gas stay the same in these kind of problems. And if that's true, well, then you can just drop the number of moles of gas from both sides of this relationship, and then you get the equation that's now written on the bottom. Say if you had the number of moles and the volume constant, so you're in some sort of constant volume container, well, then the pressure divided by the temperature before and the pressure divided by the temperature after whatever change you're making are the same. And so this would allow you to answer a question like, okay, the temperature changes from this temperature to this temperature. How does the pressure change? If you have the old pressure, can you find the new pressure? Yes, using this equation right here. So here's a different example. So we have 4 liters of gas. It's initially at 25 Celsius and 1 atmosphere. And then this gas is heated at constant pressure to 75 degrees C. What's the final volume of the gas? Okay, so how do we go about this problem? So the first thing we're going to do is write down this equation that the pressure volume divided by number of moles temperature for the before and the after cases are equal to each other. Now we can look at this and decide what to cross out. Well, it says heated at constant pressure, which means that the pressure before is equal to the pressure after. And since pressure before and pressure after are both on the top of their respective fractions, you can cross them out. All right, what else is not changing? Well, there's not really any wording in this problem to imply that the number of moles change. So that means we can say that the number of moles before and after does not change. Usually it's pretty explicit if the number of moles change, because that's something that you really have to work at in order to make happen. Okay, so now we can rewrite the equation this way. Before we continue and start plugging numbers in here, we need to first realize that when doing this equation, any units are okay because they're the same before and after and that the equality is still valid, except when you're using Celsius or Fahrenheit. And the reason here is the difference between 25 and 75 Celsius is like 3 times, whereas the difference between the values in Kelvin is much smaller. And so your math is going to be much, much different when you're taking ratios like this. So you always have to use Kelvin because the version in Celsius, first of all, isn't centered properly for like an absolute temperature scale. And secondly, the version in Celsius, you can easily go positive or negative, and then you have a negative sign in this equation, and you might solve for a negative volume, which doesn't make any sense. So, okay, got to use Kelvin. So when in doubt, convert to Kelvin. So here's the process for the temperature before and the temperature after. Here's their values both in Kelvin. Okay, so now we have our equation again, and I've taken out the things that we crossed out, and then you plug some numbers in. You have 4 liters divided by the temperature before, and we're solving for the new volume after this change, and the temperature afterwards is on the bottom, both in Kelvin. And this gives you the volume of 4.67 liters. So that's what you would get from this problem. Okay, 4 liters of gas gives you 4.67 liters total volume. Now with the sig figs, say for example 25 Celsius has 2 sig figs, but when you add 273 to it, then you have 3 sig figs. Because when you add or subtract, the decimal places matter, and so here you're significant up to the decimal place, and so everything to the left of the decimal is significant. After you add them together, that's still true, it's just now you have 3 sig figs instead of 2. So that gives us 3 sig figs for our overall answer. Great. One last thing to point out to again illustrate this change is, okay, if you use 25 Celsius and 75 Celsius in this problem, you would calculate the volume of 12 liters. And that's wildly incorrect compared to the actual amount that we found when we did it the right way. So ignore that, and then use this value up here as your correct answer. Okay, that's all we have for this video. Thanks for watching.